All right, so today we are going to start talking about one of the machine elements. Now that we have covered the background material for statics and failure modes, including surface failure, we're going to start to apply those concepts to machine elements and show how we can design machine elements for our required or particular application. So today we're going to talk about shafts. Shafts are in nearly all rotating equipment. They transmit torque or power, and we often see them like going from a motor or engine into the drive mechanisms, often through gears, often through belts. Shafts are typically carried in bearings, and they can be either simply supported, cantilevered, or overhung, typically. And they carry the power throughout the machine. And they show up in all sorts of machines in many applications. And so our task is to design a shaft that will survive for the desired life of the machine. And often that just translates to picking a proper diameter of a shaft. So we're going to walk through that design process and how do we get there. So before we get into the design process, though, we need to understand the shaft loads. And we say that non-rotating shafts are not shafts, but they're axles. So when we use the word shaft, what we're doing is we're actually talking about something that transmits torque, not something that is non-stationary, something that doesn't rotate. Okay, so if it doesn't rotate, it's actually just considered an axle or a round beam, like in your car axle. That shaft doesn't rotate, the wheel rotates on the bearings. Okay, so axles, they are just designed like beams. When we have shafts, though, we have to consider the loads to the shafts, and we often get bending. This is due to the transverse loads and the reaction forces. And we get torsion due to the applied torque, usually at one end of the shaft, and a reaction torque for components that are installed along the shaft. So remember from our Moore diagram that if we have a rotating shaft, in the Moore diagram, we wanted a zero shear in the middle, but it's not often the case in a shaft. But when we do have the loads that are typically applied to one side, usually through bearings, then the shaft itself will experience fully reversed bending. Okay, so we can calculate the bending stresses at that point due to the moment in the material at that point, and those are going to be our reversed loading stresses, because as it rotates, those stresses are going to oscillate and be fully reversed. And there may be a mean component, which we will deal with as well. So in this case, the approach that we're going through here, we'll consider both constant and time-varying torsional and transverse bending loads. Okay, so the applied torque causes a torsion, and then whatever we have here as it's spinning, then we'll have the bending loads as well. All right, so this is a example shaft from your book that covers most of the components that you'll find on a shaft. And the design principle that we've learned before is we want to actually minimize these sharp transitions in the cross-sectional geometry to reduce the static and dynamic stress concentrations. But in practice, particularly for shafts, we're not always able to do that because we have to locate features precisely. So in that case, we will have some stress concentrations that we have to deal with, and it will cause our overall shaft design to be larger, but that's because the design requires it, and that's what we have to do to satisfy the designs. Okay, so we can locate these features here in a precise manner, and often that's required for putting the machine together. Keys, snap rings, or cross pins. Okay, so if we have a cross pin where we have a hole that goes through the shaft, or we have a snap ring, or we have a key here, like a Woodruff key, then these require grooves in the shaft. So this is groove in this direction, and then or a groove here into the radius of the part, or a hole that goes all the way through. And each one of these is going to cause stress concentrations. Okay, so we have to make sure that those stress concentrations at those locations are within the design constraints and safety factor requirements for that design. So we really have to consider the entire design. So although designing a shaft might seem like pretty straightforward procedure, it's just important that we do the bookkeeping, go through the design process, and make sure that we don't have any unnecessarily high stresses in the design. And we can go back to the referenced material from Chapter 4 to, as much as possible, try to optimize the force flows through the shafts by using larger radii when possible. Okay, and just remember these are some pictures and some ways that we can reduce the stresses. This is what the stresses look like when we have a Woodruff key. This is if you have a key here, the key goes into the slot. Because of machining constraints, we usually have these radii at the end, and then we have these stress concentrations here. Okay. If we use a Woodruff key, the shape changes a little bit and spreads it out a little bit more. All right. So when we attach things to the shaft, we can use friction instead of keys and pins, using a clamp collar, and instead of a key or a pin. And these clamp collars allow this material to compress around it. So we have these slots here, so when we attach them, we get high compression, and that high compression, higher compressive forces here, increases the friction force between them. And then we can also use split collars, which are kind of like a collet, or where you have two sides that separate and you bolt them together, or shrink fits, where you heat up the part you're trying to fit on the shaft, and then drop it on the shaft and let it cool, and then take advantage of the thermal expansion and contraction for that press fit. In either case, in all cases, you have to have sufficient friction to prevent that slipping. So, and you can get into the analysis here to make sure you have sufficient friction for that. Okay. Usually we use rolling element bearings, obviously, for transmitting, for allowing rotation on the shaft, to allow it to rotate freely. But the bearings themselves are often press fit. Okay. And so what that means is we usually have to get that dimension and down to the tolerance required, and that usually means that shafts are often machined with turning machine. Okay. When you put something in service, it's going to experience changes in temperature, and you have to account for the thermal stresses as well that you might see in the machine. So one of the ways to account for the thermal stresses is to actually introduce a little bit of clearance. As you see here, there's a small axial clearance. So as the shaft gets hot, it allows it to locate it on one side and then thermally grow on the other side. So in general, you want to avoid situations like this where you have an overhung beam, because that will increase the bending stresses versus simply supported beams. But in reality, it's not always practical for us to have to avoid overhung beams, because we have to be able to remove components. And you can see this by shafts and pulleys that are on the front of an engine. They have to be serviceable. In order for them to be serviceable, you got to be able to take them apart, and you can't get into the engine and take the entire crankshaft assembly or whatever apart. Okay, so again, the design function often can trump sort of the design general principle. Okay, so that, and then when we have to make those trade-offs, we obviously would try to minimize the bending moment by making the overhung portion of that beam as small as possible. Okay, and here's just an example of where we'd have a V-belt pulley sheave here that has to be removed. So what materials do we want to use for shafts? So in general, we want to have very high modulus of elasticity materials. Okay, that makes them stiffer. So that means for the same load, if you have a higher Young's modulus, then you have less deflection. Okay, so then if we want the shaft to be as rigid as possible, we in general want to have a high modulus of elasticity. High modulus of elasticity materials that are relatively inexpensive are steel, and these are often used for shaft design. Sometimes brass or stainless steels are used for corrosive environments, but in general, most machine shafts are made from the low to medium carbon steel that is either hot or cold rolled. In general, cold rolled steel is used with smaller diameter shafts, so less than 3 inches, and hot rolled steel is often used for larger diameter shafts. When you have cold rolled steel, it introduces residual tensile stress, which can reduce the fatigue life. Not only that, but those residual stresses can cause deformation when the shaft is machined, because as you remove material, you relieve some of those stresses, and it can cause those shafts to move. Hot rolled shafts typically have a carburized layer due to the hard rolling, where we have excessive carbon in the outer layer, which it makes it harder, and they often have to be, that outer material usually has to be removed to remove that layer. Pre-hardened ground shafts are readily available, and you can machine them and then harden them. Okay, so you can get a material that might have a pH at the end of it, which means pre-hardened, and they're ground, so then you can machine them, you get your precise geometries, and then after you're done, you can send them off to heat treat to be hardened. You can also just buy hardened shafts, but in general, you can't machine the hardened shafts the shaft after it's been hardened. Okay. So let's talk about how we get the energy into the shaft, and that's through the applied torque, usually operating at some speed, and our power is just that applied torque times the speed. Okay, and omega here is in radians. Many machine applications are actually designed to run at constant speed, even though the torque and angular velocities can vary. Okay, so even though we have fluctuations throughout the process, many applications are used such that they have a essentially constant speed, and motors are designed often to run at that speed. If the relative changes in the angular speed and the torque, like the small fluctuations due to service or loading and unloading, are relatively small, then we can use the average torque values and use those for design. Typically, we'll see motors that are in horsepower in North America or kilowatts for motor power, and this is just conversion factors to go between kilowatts and horsepower and vice versa. All right, so because we have often have bending moments that are caused by transverse loads, and we have torques caused by the applied torques and the reaction torques through the gears and other components, then this causes multi-axial stress. Okay, so we can apply what we did before to find our effective stresses. Shafts can also have axial stress due to how they're loaded. Okay, so sometimes you can put a shaft in, and then you may have a nut on each side for that particular design, and when you crank the nuts down for each side respectively, then you can have an axial stress. And that's also shows up when you have vertical shafts where your gravity is coming to play, so you will have some axial stress. In general, you want to mitigate that axial stress as much as possible. One of the strategies is to use a thrust bearing close to the load, so that most of that thrust load is transmitted to the supports and not to the shaft itself. And just as we saw before, we can classify multi-axial stress as either simple multi-axial stress or complex multi-axial stress. And recall that simple multi-axial stress is where the directions of the principal alternating stress or stresses are constant with time. Okay, so that means like if you were to plot the principal stresses while the machine is rotating, that the directions of those principal stresses essentially stay constant. Okay, effectively that means that the load cycling or the load nature is such that it doesn't change the direction of those principal alternating stresses. Okay, if you have a complex multi-axial stress, then you have the directions of the principal stresses that are changing as a function of time. Okay, so this might be something where as it rotates, the loading is a function of the rotation versus a function of the rotation relative to an applied load. Okay, and so it's important to understand the state of stress, whether it's simple or multi-axial stress, when we get into our design. So how do we calculate shaft stresses? Well, we calculated them just like we've calculated them before, and that is where we find the applied stresses at all points of interest due to the applied loads. And we particularly pay attention to places where we have high stress concentration factors. And because the shafts are often put in high revolution service, then we want to calculate the alternating and mean components of the stress as well, so that we can evaluate the fatigue life. Okay, so for a typical solid cross-sectional shaft, we have these equations here, where we have the alternating loads, okay, due to an applied moment, and we have our fatigue correction factor, which we have to have our static correction factor as well, and we have our mean stresses, which are due to the average stress on that component, and in this case it's due to a bending moment using our flexure formula. Okay, so if we plug these numbers in for a solid cross-sectional shaft where the radius is half the diameter, the polar moment of inertia is pi d to the fourth over 32, and the applied torque is 16, the shear stress is 16 times the applied alternating torque, or 16 times applied mean torque over pi d cubed, then we can get our bending stresses and our shear stresses. Okay, so if we plug the values in for solid cross-sectional geometry, which is often what we use for shafts, then we find our alternating and mean bending stresses and alternating and mean shear stresses using this equation, and then we can use the von Mises criteria to find our effective stresses as well. If there's some axial load, we have to account for that, and we do that just by taking the axial load in that direction, divide by the area, and then use the stress correction factors. In this case, since we have a mean load, we have to use the stress correction factor for that mean component. So these are the stresses. This is what we have to do to get the stresses, and the moments and applied torques are going to change as a function of whatever that torque and moment is on that cross-sectional area. Okay. So, and then recall that we also need to account for the fatigue stress concentration factors and notch sensitivity. Okay. So we saw we have those three cases where we have no yielding, we have some yielding, and we have reversed yielding. Then we can modify the mean fatigue stress concentration factors according to these equations here that we went over previously. For shear, if you have shear, then you just replace your yield stress here with your shear yield strength. Okay. And recall that our fatigue concentration factors are found from our notch sensitivity and our static stress concentration factors. So we can use those either calculating an overage constant or looking at the tables that we have for that particular loading situation and geometry changes. Okay. Now, A lot of data was collected, and in the past, what's called the GO ellipse was used for design. We've actually replaced that now with the modified Goodman diagram. This is mainly for historical reference, but you can see that this is test data for steel and static and dynamic torsion with fully reversed bending stresses. Okay, so on this axis we have the fully reversed bending stresses on both axes. Okay, so when those are equal to our endurance limit, we have a 1. These have been normalized by the endurance limit. Okay, and obviously when your amplitude is equal to your endurance limit, then you have failure. And then we come all the way down here to the mean load, and in this case we have a mean torsional stress, and this is for fully reversed bending with static torsion. So if we had a constant applied torque, and we had fully reversed bending, which is a transverse load as it spins, then we get failure points that are along this graph here, and we get this equation here of the Gauss ellipse. Now notice it looks similar to those equations that we used for the modified Goodman diagram. Okay, and then historically these equations were used and where we introduced expressions that included the diameter so that we could include the loads, the yield stresses, the endurance limit, and back calculate the diameter. And we'll show you how to do that. We don't use this method anymore, but it is useful from a historical perspective to kind of understand where it comes from. Now, if we have fully reversed torsional stresses, as you see here, there's actually a little less spread in the data. Okay, and it closely follows this Gauss ellipse here. What's concerning is that when you have these static torsional stresses, you actually get failure inside this envelope. Okay, and so this method is less conservative than using the modified Goodman diagram as we've been using before, and so we'll use that. Okay, so in summary, when we do shaft design, we have to design against stress. We have to consider the stress concentration factors and the dynamic stress concentration factors, and we also have to consider deflection. So even after we go through the design, make sure the loads are okay, we may find that after we calculate the stresses at the points of interest, usually where they're the largest, then we may have excessive deflection. And obviously to calculate that, we have to have the loading functions for the beam for the shear and moment and deflection diagrams. Okay, so what that means is, just like before when we're doing real design, we often have to do the design against the loads and then investigate the deflection, and then if the deflection is too large or the loads are too large, obviously, then we have to iterate in the design, which usually effectively comes down to just selecting a larger diameter material. So these are our general shaft design considerations. Okay, so if you can, keep the shaft short. That'll minimize deflections. Avoid overhung beams or cantilever beams, and hold them on both ends in a saddle configuration if you can. If you can't, just like we saw in the example of the V-belt for an automobile engine, try to minimize the overhung length of the beam, and try to minimize those bending stresses. In general, hollow shaft, or not in general, but a hollow shaft has better stiffness to mass ratios, or specific stiffness ratios, and higher natural frequencies. And that's desirable when we talk about shaft design, because we want to avoid the natural frequencies, which we'll talk about in the next lecture. But usually, believe it or not, having a hollow shaft, even though you have more material, is actually more expensive because of the manufacturing processes required to give you that hollow shaft. Okay. We want to locate stress risers away from large bending moments if possible. Okay, so the way we do that is we calculate our loading diagram, calculate the bending moments, and then take a look at those sharp changes in cross-sectional geometry and try to keep those as far away from that max bending moment as possible. And then if we can, use larger radii and reliefs in the material to minimize those stress concentrations. If you really care about the deflection, then a low carbon steel can be a preferred material. Okay, so it's just as stiff as a more expensive material. We saw that like different alloys for steel have the same Young's modulus, but it's a lot cheaper than more expensive steel alloys. So you'll get the deflection as a requirement. The stiffness requirements, you just may not have the strength requirements. In general, deflection at the gears carried on the shaft should not exceed 5/1000ths of an inch. So what that means is when you're doing your deflection diagram, wherever, if you have a gear located on your shaft, then you really do not want that deflection at that gear to exceed 5/1000ths of an inch, because that'll cause you all sorts of problems and meshing of the gear teeth and excitation of the shaft and all that stuff. So you want to stay away from larger than 5/1000ths of an inch deflection at gears. The relative slope, okay, and again we can get the deflection from the integration of the moment diagram over EI, and then we can get the slope as the integration of the deflection diagram over EI. So we want to keep the slope between gear axis to be less than 0.03 degrees. Okay, so what that means is when your beam, when you have loads and you get your shaft deflection, you cannot have excessive deflection around the gears and gear axes, okay, or excessive slope between the gear axis. So okay, so you want to minimize the deflection and the slope. If you're using a plain bearing or sleeve bearing, okay, instead of a rolling element bearing, then the shaft deflection across that bearing length should be less than the film oil thickness. And we'll talk about the film oil thickness when we talk about bearings, but you have to keep these in mind. So in general, you don't want too much deflection, and if it's about the same price, then you'll design a shaft with a larger diameter to protect these components. In general, you want to use self-aligning rolling element bearings. Okay, so that means that as they are rolled, they actually self-align. If you're using the cheaper non-self-aligning rolling element bearings, then what you want to do is minimize the shaft deflection to about 0.04 degrees. Okay, so if you stay under 0.03 degrees in general, then you're also meeting this requirement for those bearings. If you have axial thrust loads, then what you want to do is you do not want to transmit those loads through the shaft. So you can do what's called taking them to ground through a thrust bearing. Okay, so you can design a thrust bearing in the shaft, and then the housing where you have that thrust bearing, design it so that it absorbs the thrust load. Okay. Don't split axial loads between thrust bearings, because thermal expansion of the shaft can cause high residual stresses. Okay, so you don't want to have thrust bearings on either side where you have a design where the shaft cannot thermally expand. Okay, and I know we're reading from a list, but like it's very important when we talk about design. These are the lists that you need to remember, and you need to be able to go back through when you do your design, and it'll help you get close to like a highly functioning design your first, for your first iteration. In general, the first natural frequency of the shaft should be 3 times higher than the forcing frequency. Okay, so in general, you want a higher natural frequency than the service frequency, so that way when you go up to speed, when you get up to speed, number one, you're not passing through that frequency. Number two, you're not hovering around that frequency. Okay, so in typical, you want to have a 10 times larger natural frequency than your expected forcing frequency. Okay, and that forcing frequency could be the frequency of that transverse load as it's rotating. Okay, we saw that when we have fully reversed stress, we have these stress oscillations that look like this. Okay, well, those oscillations have a frequency. So it would be terrible for us to have a loading frequency anywhere close to the natural frequency of that shaft, because it'll cause excessive wear and other problems, not to mention noise. All right, so how do we actually do the design? Well, because these shaft applications are almost always designed against fatigue, we can actually start off with our safety factor definition from the Goodman diagram. Okay, so you'll remember we had the 4 different cases, and we can use the different cases, but in this case, this is using where the case where the mean and alternating stresses maintain the same ratio. Then we can start off here with desired safety factor, okay, against fatigue in the presence of our calculated corrected alternating stresses and our corrected alternating mean stresses. Okay, we just get those from calculating the stresses and then applying our safety factors. Then we have our fatigue strength or endurance limit of that material, whatever we put there, corrected. Okay, and then we have our ultimate tensile strength. Okay, so then we calculate, in the case of alternating applied loads, fluctuating loads, and fluctuating bending, fluctuating torque and fluctuating bending, we can get our von Mises effective alternating stresses. We can do the same thing here when we have a mean stress. We can take our mean stress and axial stress, add them together, and then include the mean torsional stress to get our effective mean stress, and then we correct these with our safety factors. Okay, so if we do that, and by doing that, we introduce this d cubed term, that's our diameter. So if we solve for d in this approach, then we get an expression here that has everything that we need to design the diameter for the shaft. We have our bending stress, our applied moments from the bending stress. We have our applied torques, and these are the alternating versions, and then we have the mean or average versions from those loads, and we can just plug those values in and get an effective diameter for that design that will satisfy those criteria. So this is how we do design. Now in your book, they have a ASME method, and the ASME method is based upon the Gao ellipse. In our case, we use the modified Goodman diagram and the safety factor from that Goodman diagram because it's more conservative. Okay, so the ASME method has been abandoned in favor for this method here. And that's the method that I expect you guys to use. But in the book and for historical reference, it is in the book. And we'll do an example here where we compare what the ASME method would give you for a real design versus the using the modified Goodman diagram. Okay. If we look at the ASME method or the Gao ellipse and we superimpose it on our other fatigue failure criteria, this is what it looks like. Okay, so we have the Soderberg line, which we didn't cover in this class because we don't use it, but it is one of the fatigue life methods. And then we have the Gao ellipse. Okay, so it looks like this. Okay, it's this guy here. We have the Gerber parabola, and if you remember that's kind of what fit the average spread of the fatigue life data. And then we have our modified Goodman line here. Okay. Now what's interesting is you'll note like some of these failure criteria actually ended at the yield strength of the material. The modified Goodman line allows you to exceed your yield strength of your material, and it goes all the way to the ultimate tensile strength. But in general, you want to be below your yield strength because you don't want the material to yield, and you will get your alternating stress and your mean stress here, and we use that definition of the safety factor here to introduce our expressions for our loads, which included the diameter, so we could back out the diameter here, and it automatically included the fatigue strength and loading conditions for both alternating and mean loads for the bending stresses due to the transverse stresses and the applied torques to that shaft. Okay. All right, so let's look at an example. We'll pause here and we'll get over to start another video where we'll walk through this example, which is example 10.1 from the book.